Okay, so here's the chapter 11 homework. A bunch of these already have written examples with them, like this one does. So I don't think I'll do anything with those. I really want to go over some of the right-hand rule problems. Okay, some of these are just conceptual and should be easy. Okay, that one has a written example. Okay, so we're looking at the paths of several different particles. We want to figure out which one of these has to be a positive charge. So this is going to be a right-hand rule problem using F equals Q, V cross B. All right, I have not used my Elmo in about a year, so let me see if this works properly. Share. Oh, I stopped sharing. And why is my Elmo not working? Let me pause real quick. Okay, I still have my background on. My video was working. All right, so I'm gonna have to go back and forth here. Let's look at this problem. We have a magnetic field that's coming out of the page. So we represent that with vectors by drawing circles with dots. I'll switch to the camera view in a second. I'm just going to draw a few of these. I'm going to draw one of these. I'm going to draw D. Let's look at D. Oh, this guy's going to be upside down. Maybe I didn't pick the best one. Try to right-hand rule. Okay, so these circles with a little dot represent a vector coming out towards your eyeball. The way I was taught this was think of this like an arrow, and you're looking at the tip of the arrow, and it's just penetrating the board, and it's about to come out. If our arrow were flowing away from us, we would draw this guy, and that represents the feathers that go on the back of the arrow, and that we're seeing the very back of the arrow. This is away from you, and this means toward. So our magnetic field is coming out. I've got this charge right here. His velocity vector, say at that point right there, his velocity vector was pointing down. So it's really easy to confuse up, down, in, out, north, south versus up, down, all that. You got to be careful. I'm calling this direction out and in, not up and down, because I'm going to use up and down for this direction. So my velocity vector is flowing down, B is flowing out. Then the magnetic force would be F equals Q, V cross B, where we use the right-hand rule to figure out the direction of F. So in magnitude, that's just everybody magnituded here. And direction is perpendicular to both and determined by the right-hand rule. So you can do it by curling your fingers or using 3 fingers. I'll do the 3-finger method here. V, B, F. Your first finger points in the direction of V. So I can't go like this. I have to spin my hand around. That's why I picked a bad example to start with. V is pointing down. Now I need to rotate my hand until my middle finger lines up with B. V, B, F. B. Then F would point to the left. If this were a positive charge, F would point to the left. So I've got this velocity vector that's pointing down. If I applied a force to the left, it would curve to the left. Remember, Q here could be positive or negative. If Q was positive, this guy would have curved to the left. V cross B, here's the other method. All my fingers point in the direction of V, and I curl my fingers toward B. Curl. V cross B equals F. That guy can't be a positive charge. He has to be negative, because he's going the opposite way. If Q is a negative, you end up with the opposite force. All right, what about one of these other guys? Let's look at E. Doesn't get curled at all. Look at him. He just goes straight. He doesn't even notice the magnetic field. He's got to be a neutral charge. Look at B. He's curling to the left. He was going this way, but then he got pushed to our left, his right. If we were riding along with B, he would feel a force pointing him to his right because he's facing like down that way. B has to be positive. What about A? Let's look at A. Say that he's right here. So at this particular spot, say, like, I don't know, maybe we'll pick that. We could pick any of these. There's a velocity vector. He was going that way. So first finger in the direction of V. Hold your fingers in like an XYZ coordinate system. In fact, that's one way to remember it. If you think XYZ, and then Z would point out, X cross Y equals Z. Really, it's I hat, the vector that points in the X direction, cross J hat, the vector that points in the Y direction, is K hat. But you could think X cross Y equals Z. X cross Y equals Z. So V is the first one. I got to rotate my hand until my middle finger lines up with B. So I'm going to hold my first finger along V that way and rotate. Okay, now I'm lined up with B. Then F would point off this way. My force vector is perpendicular to both of them, perpendicular to V and perpendicular to B. So this guy was trying to go that way and he's going to get turned. He would have been turned like this if he were a positive charge. The right-hand rule assumes a positive charge. He got turned the other way, he must be a negative charge. Protons and electrons have the same electric charge, so they would experience the same magnetic force. So I'm trying to give you the answers here. They're opposite charges, so they'll get pushed in the opposite direction. Now, what about the radius of their path? That's that cyclotronic radius. Let me open another tab here. And go to our formula sheet. And you should have this in your notes already, the cyclotronic radius. Anytime a question asks you for radius from now until the end of the semester, it's probably asking for the cyclotronic radius, and that's going to be this formula. It's right up here at the top of the formula sheet. This one right here. So the cyclotronic radius, these radii we were just looking at, and that's literally what's going on in this question here. These guys would go in circles. The radius of this circle here depends on Q. Both the proton and electron have the same Q. They both were experiencing the same magnetic field, B, and I think they were both going the same initial velocity, right? Yeah, same velocity. What's going to be different then is the mass. A proton's mass is thousands of times bigger than an electron's mass. Bigger mass would be bigger radius. To the electron because it has less mass. Okay, let's do this one. So I've got, notice we got an electron. So there are two different ways you could deal with electrons. You could use your left hand. Positive charges follow the right hand rule. You could say negative charges follow the left hand rule. But I'm left-handed. And if I start using my left hand to do a problem, I'm going to goof and I'm just going to keep using my left hand on all the problems. I won't remember to go back. So what I do is I just do my right hand rule. And if it's an electron, whatever answer I get, I flip it over. Okay, so F is Q V cross B. I'm going to forget about him being negative for a minute. I'm going to do V cross B. So V is pointing down toward me. B is up. So V, B, F is the way a positive charge would move. A positive charge would get pushed to the left, but he's a negative charge, so it's going to be to the right. Might be doing too many of these for you. Okay, same kind of idea here. Notice we've got 4 different questions, 5 different, a bunch of different questions there. Those are all good questions. Okay, this one. This is a good question. I don't think I have a written solution to it now. So I've got a couple of different competing things going on. You might have a similar problem to this where you have maybe a magnetic field and gravity, and we want to maybe balance something out, find the correct magnetic field to balance up a charge against gravity. Here we've got both a magnetic field and an electric field. So we're going to have to find the force from both as vectors and add the vectors together. Now, I think this problem is set up so that these vectors that we get are either parallel or anti-parallel. So we can either just add the numbers or subtract them. We don't have to like find an angle or anything like that. So let's take a look at this one. And I'm not going to work out the numbers for you. I just want to help you conceptually. So let's see, we've got B coming out of the board at us. E points straight up. I can even want to color code it the same way they did. And then I've got a positive charge right there, and it even says positive, moving to the right with some velocity vector. Okay, so for B, FB, the magnetic force will be Q V cross B in magnitude. So just take everybody's magnitude. Just multiply the 3 numbers together. I think they're even all positive here. Well, I mean, velocity is a vector, so we want speed. That's what that means. So we just multiply all those together. What about the direction? V, I got to spin my hand around like this so that my middle finger points in the direction of B, then my thumb points in the direction of the force. So FB is going to point down. This only gives me the magnitude. If I set up a coordinate system here, say some y-axis, FB is going to point in the negative y direction. So FB is going to be negative that number. Okay, what about the electric force? Fe is Q times the electric field. There's no cross product here. It's just Q times E. Q was positive, so the electric force points in the same direction as E. Magnetic forces are always perpendicular to your field. Electric forces are always parallel or anti-parallel to your field. So this guy's going to point up. So Fe will be some positive, excuse me, Q times magnitude of E. And I don't know which one's going to be bigger. We'd have to calculate both numbers and see. I don't know if the net force is going to be up or down. Depends on in magnitude which of those is bigger. But we'll just add those numbers together. So that's what we're doing. We're one part at a time there. The similar question there, only now we're looking for okay, so notice here we're going without deflection. So I've got two different forces pushing on this charge, but neither one wins. So just think about that for a second. What are E and B going to have to do so that neither one wins? And then using the same formulas we have here, calculate the velocity that would make that happen. If the velocity were 0, by the way, stationary charges don't even notice a magnetic field. They don't even know it's there. If V equals 0, FB would be 0, and this guy would only feel the electric force, and he would move toward the positive plate. Or, sorry, no, he would move in the direction of E. He would move toward the negative plate. So V is not 0. Oh, and look, there's a written example. Okay, and then that one has a written example. Okay, I think that's good. I think that'll get you through this assignment. All right, let's stop recording there.